Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you. Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up. And check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Before we begin, a note from our sponsor. I'm Richard Jacobs, Executive Director of the nonprofit Finding Genius Foundation and host of the Finding Genius Podcast. In late 2016, I was rear-ended at 65 miles an hour by a truck on the highway, which sent me off-road into a ditch. The impact of the collision gave me a concussion and other injuries. At the hospital, a CT scan showed that I had thyroid nodules, which turned out to be cancer. It was then, when I had a biopsy of my neck, that I realized even if I was a millionaire, I wouldn't want a second or a third biopsy due to the pain and the invasiveness of it. And appointments at that time for thyroid experts were 3 to 6 months out. And I was worried about dying now, even if that was irrational. So because of this, I've decided to raise money to conduct a literature review on steroids, on the causes of anxiety and depression, a condition that affects well over 50 million people in the United States and hundreds of millions worldwide. Our goal is to create a codex, a guide that reveals all possible treatments for anxiety and depression for people that live with the condition, or for loved ones that have it, as my wife and my son do. To find out more about our fundraiser, visit findinggeniusfoundation.org and click on Current Initiatives. And now, to our guest.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. I have Andrey Ethan Rubin, Ph.D. He's part of the Student Zucker Lab, Department of Environmental Science at Tel Aviv University in Israel. We're going to talk about microplastics. So, Andrey, thank you for coming.
Thank you for inviting me.
Yeah, if you would, tell me a bit about your research. What are you working on right now?
Okay, so I think that we will start from the beginning because I'm not sure if everyone aware or know about microplastics. So basically, we're talking about very tiny particles made of plastic, usually in a size that is smaller than 5 micrometers. And those plastic particles basically can be found anywhere. We have an evidence that they can be found in our water, in our food, in our land, in our air, and recent studies shows that it can be even transferred to the remote areas such as the North Pole. So all of us surrounded by those particles, and for us and our group, it was interesting to ask a question of, okay, so we have those plastics particles all around. What will be the effect for them? Like, what will be the effect of them to humans, especially for our intestinal gut cells? So our research specifically, and the last paper that we published, is dealing with the question, what's going to be if we're going to look at the microplastic as more complex compared to the just a simple particle. Because basically after that particle goes to the water, for example, it can interact with other environmental pollutants. And in our case, we used a model in which we take in microplastics. We interact them with other contaminants from the environment. In our case, it was triclosan. And we were interested to see what will be the effect of the combination between the two. Does microplastic somehow can increase the toxicity towards cells, or it's not really matter? And the results were pretty interesting because we saw that basically microplastic can act as, let's say, kind of magnet to those pollutants, and he can absorb them on his surface. And then after he gets into our body, he can release them very close to our cells and then cause toxicity in a very, very high ranges compared to the small amounts that are present.
So microplastics act as what, nucleation sites for other pollutants? They aggregate them?
Exactly. They can absorb them. And by the way, it's true not only for organic pollutants. We have a lot of evidence that microplastic can absorb heavy metals. We know right now that microplastics is a kind of habitat for viruses and for bacteria and for other aquatic creatures that can just stick on their surface. And it can be very dangerous because, for example, in some cases, viruses or bacteria that absorb on top of plastics can be pathogenic, and then they can cause severe illness after we eat them, for example.
So there must be many different kinds of microplastics, fibers versus other short, jagged, crystalline shapes. Which shapes seem to be the ones that trap the most stuff? Or are there certain shapes that viruses tend to work better with versus other substances?
So let's say that other than only a shape, there is also a lot of matters that can impact that absorption phenomena. For example, we know that after microplastics are just being in the environment, they oxidize by the UV radiation from the sun. And then on top of their surface, there is a carboxylic group that insert to the surface. They are not appears in a natural microplastics. It's something that the nature do for those microplastics after the weathering procedure. And then we see that, for example, microplastics that been weathered and having carboxylic groups can absorb much better compared to the pristine particles without any carboxylic group on them. And it also, by the way, true for our research. We took a pristine particle and we took a particle with carboxylic group, and we showed that basically the differences are huge. We can absorb much more of the contaminant on top of the plastic particles that have those carboxylic groups.
So what's the functionality of these side groups? Are they what's the analog in more natural substances of that? What is it, like carboxylic acid? Or what do these groups sound like? Or what do they do functionally?
So basically, if we're trying to simplify this, try to realize that you have a flat surface and you have a surface with a certain roughnesses which can chemically interact with other substances. So carboxylic group, they are basically an addition, a chemical addition of chemical groups that can interact chemically with other pollutants, which are, once again, not exist in a pristine form. They exist only in a weathered form. of plastic. And then after that weathering, we have more and more carboxylic group, which can interact with more and more pollutants. And if we have microplastic weathered for, let's say, 10 years, it will be much more reactive compared to plastic that was released to the environment just a year ago. So
but what does this tell you? What does this tell you about the weathering process? How fast do these groups accumulate, and how do they accumulate?
So it depends, because there is solar irradiation is not equal around the globe, and we have areas in which the solar radiation is much more intense compared to the others. For example, here in Israel, we see that the irradiation is pretty high. So our plastic weathered really quick, and we achieved those carboxylic group in few months. So basically, plastic weathered few months under the Israeli environment can be much more toxic compared to pristine forms.
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now, back to the show.
Do you know anyone that has taken plastic bottles or other kinds of plastics and maybe put them in a chamber with some water and sun, and it's sloshing around and bouncing around, maybe with sand in it, to try to emulate how the weathering process occurs? Do you know how long it takes for different plastics? Has anyone modeled that?
Yeah, so it's hard to, let's say, 100% mimic the environment, because other than sun and, let's say, physical factors, there is also the biological factor, which is crucial. Because, for example, even like if we're going to the aquatic environment, so there is also a very high presence of all kinds of bacteria or algae, which can stick to the surface and can degrade it, and also create, by the way, those carboxylic groups. So if we want to imitate the nature in 100%, so let's say it will be almost impossible. There is a lot of options of imitate a part of it, in which you can use that weathering chamber, as you mentioned, which can have a certain UV radiation, a certain heat, a certain wave speed, because it's also matters. All of those factors are matters. So you can somehow simulate it. It will be never 100%, but still, for example, in our previous work, we tried to do that, and we used a lab approach, which is kind of mimicking the environmental forces, the mechanical forces of the waves, the solar radiation using a UV lamp, and also the heat from also solar radiation using an oven. And we create like a prototype of protocol that can be used to create microplastics with a bit higher environmental relevancy compared to the models that are using now, because now a lot of people are just using spherical beads, like synthetic beads, and they are not really represent the environment.
Yeah, even though you don't know exactly how long the weathering takes, it's good to get approximations. So have you studied fibers versus, plastic number 5 or plastic number 3, or, drinking plastics from, let's say, a 2-liter bottle versus, again, fibers, to see how long each takes to create and how long each takes to form these functional groups, these carboxylic groups? Has anyone done that and figured that out?
So in our case, we use only one type of plastic, and they are a rounded plastic made of polystyrene as a model. we didn't use any other like fibers and stuff like that, but it can be also used, like we can multiply our study to other shapes and our other forms of microplastics. In generally speaking, we see that in the environment, for example, we have a lot of fibers, especially from wastewater treatment plants, because we have a lot of fibers from our textile. Most of them are removed by the wastewater treatment plants, but still there is some portion that's released into the environment. We didn't do the fibers once again, but it can be really interesting to do that with fibers as well.
Okay. So what are you guys trying to figure out specifically? What is your research about?
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
So our approach is to look at plastic particles, at microplastic particles, as an, let's say, holistic model, not look only at the particle itself, but also take into consideration other factors. In our case, it was a factor of other organic pollutants. And we showed that the combination of microplastics together with micropollutants that sorb on top of them, increasing dramatically the toxicity. It's very important to take into consideration the fact that microplastics are never alone as a particle. They have a certain layer, which is called an eco-corona, or there is other call it protein corona. And that layer is a very, let's say, complex structure. It contains metals, it contains an organic pollutants, it contains bacteria. And to have a better estimation of microplastic and the hazard that they're holding, we have to do complex models of microplastic and use them to estimate the toxicity. Because otherwise, if we're using only the particles themselves, we're not really representing the environmental microplastic. So in our case, it was a little step forward into more complex models. We took, once again, microplastics and micropollutants, and we showed that that combination is much more toxic compared only particles.
So do microplastics, they attract all these pollutants, but do they also agglomerate together? Do they attract each other? Or does each one become like a city unto itself, or a pseudo cell unto itself with the core of the microplastic, and then all the functional groups and bacteria and viruses and metals and all that on the outside, like your corona, like you said?
Yeah, so it's a very interesting question. I think in the environment, we don't see a lot of, let's say, sticked plastic particles each to other, but I think that it can happen in our body because, for example, because microplastics are very hydrophobic, so they can interact with other hydrophobic substances in our blood, for example, because microplastics, it's known now that microplastics can get into our bloodstream. So, for example, they can interact with the fat or with our proteins, and then can basically block part of our bloodstream.
That's crazy. So have people found them in atherosclerotic plaques, like in the walls of people's blood vessels, like part of plaques, or are they more free-floating?
Yeah, so wasn't found as a flux yet, but there is a very interesting study published recently showing that we have a lot of microplastics in the blood. They gave an general estimation of microplastics. They are not talking about their shape or where that they found. They just told that, for example, microplastics made of PET, which is polyethylene terephthalate, a polymer which is origin from, for example, single-use bottles of water. So that polymer was found in very high percentage compared to the others. And that means that for example, if we're drinking a bottled water that was on a sun or just degrade, so those plastics can get into our stomach and then get into our bloodstream, and maybe sometime like in the future we'll also discover that they can block our vessels, and together with other substances in the bloodstream can create those blocks.
Do you know anyone that's studying cancer and microplastics? Like, for instance, do microplastics comprise, the core of tumors? Is anyone looking at that?
So in terms of cancer, the interesting thing is that the previous stage of cancer is a constant inflammation. And in this case, there is a very also interesting study published recently, showed that for people who's having, I don't remember the exact name of the illness, but it was kind of inflammatory disease. So people who've been exposed to higher amounts of microplastics, they having more chance to have that inflammatory disease. It was studied by the amount of microplastic found in their stool. So, for example, people with chronic inflammatory have much higher amounts of microplastics. So it's not direct still, but we can have a clue and understand that there is some connection between a high presence of microplastics, either if it's in our blood or in our stool, or doesn't matter, between illnesses. And because we're exposed to microplastics from, once again, all the variety of factors, like we're breathing it, we're eating it, even if it's very low amounts, a chronic inflammatory diseases, which can take 10 years, for example, and may be a precursor for cancer, it's a scenario that for sure can happen.
Yeah, I would guess that people that are inflamed have a more leaky gut, and so the microplastics probably get through their gut lumen into their bloodstream more readily. Maybe that's why that's happening.
Yeah, definitely. It can be because of that, or it can be, for example, in terms of mechanism of toxicity, we know that microplastic can create a radical form called ROS, reactive oxygen species. So those ROS can create an inflammatory diseases as well. So we still don't know what is the exact reason. We have some correlation between those factors, between the amount of microplastics and inflammatory diseases. We have a lot of evidence about the potential of microplastic to create a ROS forms of reactive oxygen species. So there is a lot of, let's say, enigmas in that field of microplastics, because it's, let's say, relatively new contaminant for humans. We're exposed to it massively from the 70s, more or less, and we still don't know all the potential effects, because we expose it in very small amounts, and a chronic disease, as I said, can take 10 years or even more to detect. So I guess that in the future we'll know much better and understand microplastics in a better way.
The microplastics start out as macroplastics for the most part, I would think.
Yeah.
Why do you think that? Do they become more and more active the smaller they get? And let's say once they get to 5 microns and below, maybe the exterior charge of the valence electrons, creates it gets concentrated once they get to these small sizes and morphologies. Maybe that's how it's then able to attract these other chemicals. I mean, do you see on larger pieces of plastic that they have as many active sites and they attract all this stuff? Or is this like a size at which this tends to happen more often?
So we know from toxicology that as lower the size is, you have much higher toxicity effect, only based on the size. And this is related to two different reasons. The first of them is that if we degrade in a size, we have a much higher surface area of the particle, and then it means that much more surface can interact with other contaminants, for example. So as lower the particle is, it can be more, let's say, interactive with the environment. And it's also true, for example, for nanoplastics. We see that if we degrade microplastics to nanoplastic, which are even smaller particles, now we're talking about particles smaller than 100 nanometers. So in that case, they are extremely toxic compared to the microplastics. So as size is decreased, the toxicity is increased. It's a connection between the size and the toxicity. The other thing is that we need to remember that basically the size of the particles is also dictate their ability to enter the cell. For example, if we're talking about big plastics, so they cannot get into our cells because there is a membrane blocking them. Same for microplastics. They are still too big to get in. But if we're talking, for example, about nanoplastic, in that case, those particles are small enough to get into our cells using a different types of mechanism. For example, endocytosis is one of them. Those particles are sticks to the membrane and then create a kind of sphere that can be inserted into the cell, and then this plastic particle basically now is inside the cell. So try to imagine if you have nanoplastics that can that have the potential to get into our cell from inside, and also holding, for example, let's say, a certain amount of pollutants. So in that case, we're increasing the toxicity in very high numbers.
So what are some of your current projects? What are you trying to figure out at this moment in the lab? What are some of the projects?
So we're working on a few projects right now, and part of them related to understand or have a better estimation on the toxicity that microplastic can cause, not only for humans, but also for aquatic creature. And we have collaboration with other colleagues which are working on the aquatic creature that can be also exposed to those microplastics. And we're trying to understand that what will be the effect of microplastics on them. We also have a collaboration a team working on plants, and we're trying to understand how plants interact with microplastics. And also we have a team which is doing monitoring of microplastics, because it's also important to know what are the enemies outside who want to characterize the microplastics that appears here in the, for example, the Mediterranean Sea. We want to characterize them to know which polymer they are made of, what kind of, for example, metals sorbed on them under environmental conditions. In that case, it's a real microplastics from the environment that we isolate and analyze. And that's it.
Are you studying microplastics at all in the field? Do you go out and take samples, or are you doing it all in the lab with these round particles?
So part of our studies are lab-based, and we test the microplastics under lab conditions, and part of them are a monitoring of microplastics from the environment, because it's important to have those both sides. Like, we want to understand what kind of weathering happens to the microplastics, how the microplastics change under environmental conditions. And we want to apply all of that knowledge, let's say, on our model, which is a synthetic model of microplastic. And we kind of trying to get into closer similarity between the real environmental microplastic and the synthetic model that we are creating in the lab. And here is your opportunity to ask me, so why you are not just using a microplastic from the environment for your studies? And the question for that, thank you for the question, by the way, it will be that microplastics from the environment, as I said before, they are huge metrics of different types of stuff. First of all, in the environment, you have different types of polymers. Microplastics are not only one polymer, it's a variety of polymers. They have a different shapes, they have a different chemicals inside of them, because each plastic product contains also a chemicals, not only the polymer. So this is also changed. We have a lot of different pollutants that absorb on them, and it's really hard to estimate that system when you have so much factors that changed. So we're trying to kind of, let's say, synthesize a model which will be controlled from one side, but still will be relevant to the environment.
I know the outside environment is incredibly complicated, so you're trying to do a reductionist type approach in the lab, see if you could figure out some principles and then apply them to the environment.
Exactly.
Right? Have you seen microplastics accumulate biofilms in the wild? Like, what have you observed in the wild that they accumulate? Do they tend to associate with each other, the different microplastics, and do their epicoronas bond or form like a film or anything? Or again, do bacteria form biofilms on them?
Yeah, so from the monitoring that we did here in the Mediterranean, and also from a literature, by the way, we see that microplastics are kind of an ecosphere of a different environmental creatures. It can be a bacteria, but it can be also an algae. And for example, in our samples, we see a lot of diatoms, which is a kind of algae which sticks to the surface of the microplastics. And basically, it's a kind of ecosphere by itself. That single particle in the size of few microns or even lower is an ecosystem that contains a huge amount of different living forms.
Is there a certain size that either bacteria or other creatures eat? Do any of these creatures, use the microplastics as a food source and actively, bite pieces off of them or feed on them? Or is it just a nucleation site where they attach and hang out and that's their base of operations?
Yeah, so for bacteria and also for certain types of algae, microplastics can be a carbon source, but in most of the cases, the bacteria or the algae doesn't have the exact set of enzymes that can fully degrade the plastic. So what they are usually do, they kind of scratch the surface of the plastic. They get a certain part of the surface of the plastic, but they are not degraded all. So we see that bacteria are doing that procedure. They degrade the surface of the microplastic. They stick to the roughness, to the holes that they are creating, and then they survive there. It's still not sufficient enough, and that's why we have a lot of microplastics in the environment, because the environment is not adapt or fully adapt to degrade microplastics. There are some studies that showing that bacteria can degrade a certain types of microplastics, but unfortunately, it's not something that can create, like, it's not something that can be happened under environmental conditions. That's why we still have a lot of microplastics in our oceans and overall, like, in the entire world.
What questions are you trying to answer going forward in the future? What is your lab trying to figure out?
So other than the studies on the plants and the aquatic creatures that I mentioned before, we're trying to build a bit more complex model of microplastics, and that time we want also apply the biological part and see how presence of a certain part of bacteria can increase or change the interaction with cells. And in our case, we are working on immune cells, and from preliminary data that I have, it seems like other than cause a toxicity for immune system cells act differently to microplastics. And it's a very interesting phenomenon. I hope that we'll be able to investigate deeper and hopefully also publish a good paper and interesting research on it.
Okay, well, very good. So what's the best way for people to find out more about your work? Where can they go?
So if you type Google, by Google Andrey Ethan Rubin, you'll find me in social medias, and you can find me in Twitter and ResearchGate. And you can also type Zucker Lab, which is the lab that I'm working in, and you can get all the information. And we're more than happy to provide those informations for the public. And also we're seeking for collaborations from all around the world. So if there are listeners that are thinking about collaboration in the plastics research studies, I'm more than welcome to send an email or use in other ways.
Very good. Well, Andrey, thank you for coming on the podcast. I appreciate it.
Thank you very much, and have a great day.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.